Today I'm going to explain how Kmap works and how they can be used to minimize the terms and literals in Boolean expressions. First, I would like to explain why do we need to minimize the terms, or why do we need to simplify the Boolean expression? Why can't we leave it alone as it is, as sum of products or products of sum? Well, there's a couple of good reasons that we need to do so. First, the cost. The cost of the circuit will be reduced when we reduce the Boolean expression or simplifier. So it means when you have less literals or less terms, that means that we have less gates in the circuit. So it means that we have to pay less to buy these parts and connect them together. And then also that the performance will be optimized. It means that when you have less gates, it means that you will have less delay between the signals that is being outputted or inputted to then outputted. So it means in real world is that you will have a better processor and then also a cheaper processor that does exactly the same thing. So the Boolean expression, the Boolean algebra is just an abstraction of what is actually there. So here we are just studying the abstraction, which is the Boolean expression. Then we are minimizing. Then it's actually implemented using gates. So there is actually a very good game that deals with topic with digital logic design that I would like to show you before we begin in Kmaps. So this is the game I'm talking about. So this is one of the functions that we'll be optimizing, that we will be hopefully optimizing and simplifying its Boolean expression. So you see here on this side. So this is the function. So this is the function. Here you have the output. Here you have the input, and then here you have the output, which is this small, either green or red. So here when you are changing here, so for example when you have one, here as in binary, when you have two, so here you have three, so it is off. When you have two, it is on. So this is the min terms of the function. So you see this is a circuit that's actually implemented using the Boolean expression. However, you see how complicated this function is. And here also, if I click here, you see the delay on each one of these gates. So in each one of these AND gates or the OR gates, it's actually a delay. So it means from this signal that is coming from this line to actually outputting here, it has to go through many gates. That means more delay. However, see after we simplify this, this whole thing, we can get this small one. So here when you have 3, it will be off. When you have 2, it is on. So these two circuits are actually identical. So this circuit is identical to all of this, to all of this here. So that's why we use either Boolean algebra to simplify the Boolean expression, or we use the Kmaps or other methods to simplify it. So that is the reason. First, we will have less gates, so it means that cost will be less. So it means the parts or the circuit will be easier to implement, and also the performance will be much better, because you see here the delay will be much less. So the signal has to travel through less amount of gates. So it means the signal is traveling faster. And that means that it is of better performance. And that's it. That is just a simple example. Now imagine if you have millions and millions and millions of gates, or you could say transistors in the CPU, which is the CPUs that's used, or let's say microprocessor. So optimizing the circuit is essential to ensure that the circuit is running as of lowest delay as possible and also as cheap as possible, because that's what is the market demands. We want something to be fast and as well to be cheap. So that's why are these methods in Boolean algebra or Boolean algebra simplification, or actually Kmaps or other software that use other methods that are used to minimize the circuit. And this is what's all the chapter 3 about, is gate level minimization. How can we minimize the amount of gates in circuits that does exactly the same thing? So here you see this huge circuit is exactly like this circuit, exactly. We mean exactly to the point. So any combinations or any possibilities of four inputs of these will output exactly like this. So of course we would like to find the solution for each of these circuits that will give us the least amount of gates used and the better performance. And that's it. Hopefully I did not take too long in the introduction. I just want to give a little bit of appreciation of what is actually the use of K-maps and why do we actually simplify it and give a better big view or big picture on the topic itself. So now let's dive in how to use K-map to optimize circuits. So first, let's begin with two variable function. So here we have two variables. So there is a couple of rules that we have to follow. In K-maps. First, let's set up the K-maps and see how it is actually done. So first, we need here for two variables we have four possibilities. So here the amount of possibilities in any amount of variables is just determined very easily. So amount of possibilities means like how many possibilities you can have is 2 to the power n. In our case, we have here 2 to the power 2, which is two variables. Here you have 2 to the power 2, so it means you have four possibilities. You see here from 0 to 3, that means that you have four possibilities. So first, the way you set up, either you choose A to be in the vertical, which is here the rows, or the horizontal, which is the columns. So let's choose, for example, A to be here, and the choice is arbitrary, so it doesn't really matter. But you have to make sure you follow it. So first, you write here then 1 is 0, then you write 1, and then you have 0, then 1. Okay. Then I would like you to write. This is a personal method I use to not get confused, especially when variables get a bit larger. So when you get to 3 or 4, I'd like to use this method. So let's illustrate the method. The method is very simple. So first, you write here on the side of the table, you write 0, 0, then 1, then 2, then 3. So these are the possibilities. So here when it is 0, when it is 1, 2, or 3. Okay? Or here you could say that m of 0, m of 1, m of 2, and m of 3. So if you study the book, you use this notation. Okay? Then you write these values. So first, and this is just to illustrate, this represents 0, which is just the value 0 here, then here 1, which is the value 1, and then 2, the value 2, and then 3, the value 3, which is in binary. Okay, then you fill in the table. So we have here, first when you have 0, 0, it is going to be 0, which is the first here 0, then you have 1, and then you have 1, and then you have 1. Okay? Okay. Now we have constructed the K-maps successfully, and it's actually pretty easy for two variables. Now what are the rules? What is the purpose of it? That is the question. Why do we need to construct it? How can we use it? Well, let's put it in this way. The goal of K-maps is to create groups or relationship between cells or adjacent, let's say cells or adjacent cells. So how can we create groups and then write the function for it? So we need to create groups that are gonna be used to create to write the function, which is the simplified function that we are looking for. So how to do such a thing? First, there are a couple of rules. These rules are very important, even though they are a bit long. But once you apply these rules, they will become very easy because you just know these rules and apply them in doing the problems. So let's go over these rules. Okay. So we have, let's make this a bit bigger. So we have here. So the first rule, group may not include any cell containing 0. So it means that when you are grouping two elements, so this is the purpose of K-maps. In this stage, we need to group these two elements together to create the function. So here it says that may not include 0 containing any cell containing a 0. So this is illustrated. When you group 1 and 0, it is wrong. You have to group either just 0 or just ones. So you cannot mix between these two things. So here, let's imagine if there is a 0, I can group these two together. But if I cannot do such a thing, so that's it. Again, and also if you group zeros, there it is another method. It is not using the max terms, and that is another thing. We will be focusing in this tutorial. We'll be focusing only on the grouping ones. Okay. The second rule here: group may be horizontal or vertical, but not diagonal. So it means you only can group in in a vertical or horizontal manner. You cannot group them diagonally. Like if you have here, you cannot group such a thing. You cannot do such a thing. Okay. Now here, this is a very important rule that I have just, let's illustrate it on here. Okay. Grouping in the values. So here, let's say you have, let's say this. First, the grouping number, how many cells can you group in one group, is determined exactly by this formula, which is 2 to the power n. So we have here, when you fill in the value of n, you will have either 1 or 2 or 4 or 8. So these are the only combinations of amount of cells in group that must exist. So let's illustrate. What do I mean by that? Let's go to the website again. So here it says that's group of 3. That does not follow the sense, which is 1 and 2 and 4 and 8. So this is, you cannot have a group of 3, you cannot have a group of 5, you cannot have a group of 6 or 7. Only on these values. So this is a group of 2, so it means it's okay. You have a group of 4, it is okay. Here you see you have a group of how much? You have a group of 5. And also it's not a group, to be honest. Here it does not illustrate it very well. Here it has grouped 1 and zeros, which contradicts with the first rule, which is cells should not include 1. But even if these are ones, it's actually, if this is 1, then it becomes 8. So it will be okay. But let's say, for example, it does such a thing like this, which is going over here and then here. Then group of 5 does not exist. So you should be very careful when you are choosing a group. There must be a multiple of the 2 to the power n. So 2 to the power, choose 1 or 2 or 4 or 8 or 16 and so on. Okay. So sometimes it's tempting just to choose 3, but that is incorrect. You have to choose multiple of power 2 to the power n. Then we go to the rule after, which is each group should be as large as possible. Well, this is also a very good rule. Well, here you have, this is the table and this is the table, which is all identical. You have one grouping, is that you have group of 4 and then group of 4 as well. But in this grouping you have 1 and then you have 2, a group of 2, group of 2, group of 2. Well, this grouping is technically is not incorrect, but it is not the most minimized that you can get, because here it's very important to note that the larger the group is, the less amount of literals that you will have, the less amount of variables that you will have in each term. So here, the worst you could do is just group 1 and 1 and 1 and 1. It means that in each variable, in each cell, you will have 3 variables, and you will have how many terms? You will have 1 term, 2 term, 3 term, 4, 6, 7 terms. But if you group 2, you will have 2 variables, 1 and 3 terms. But however, if you group 4, you will have 1 variable. That means you have 2 terms with each with 1 variable. So a very important rule to follow is that you must have always the large amount of possible. Each group should be as large as possible. So it means that you need to minimize the amount of groups in the table. So that is what is trying to convey in this rule. Like each cell containing a was must be at least in one group. Yeah. So this is very important as well. If you have 1 here or 1 here, then it must be grouped at least once in the group. So you cannot leave 1 alone. You have to group it at least once. And that's it. And then you have groups may overlap, so overlapping group is fine. And then you have what as well? Group around the table. Around the table, yes. And this is also very important. Here let's do a group, let's do a table for 3. A table of 3 variables. So 3 tables, which is gonna look something like this, just to illustrate this point. So going over like this and then going over like this. So what is the rule talking about? The rule is talking is that this cell and this cell is actually adjacent to these cells. So this cell is adjacent to this. So you can think of it as like as a cylinder. So as a cylinder going around. So here, you imagine that this paper or this plane is actually wrapped around itself, and if you wrap it around itself, this end will touch this end. So it means that this cell is adjacent actually to this cell. It's next to it. And also I want you to think as well that this, and when you go to 4, so let's write it, when you go to 4, which is 4 variables, the table will look something like this. You have, the table will look something like this. Also, these are adjacent to these. So we can group these together. So I want you to think of this plane as actually a sphere that is connected across. So if you fold this plane in this side, these two together, these 2 points, this here, this point, and this point will touch each other. So it means that you will have them adjacent to each other. And if you fold this side with this side, you will have this point as well touching this. So that is what we mean by that you can group this with this. So this is actually adjacent with this, and this adjacent with this, and this is adjacent with this. This will become very important when you go to 4 variables or 3 variables, because we can group in much better way if we know how to do this. Finally, one thing about grouping is that if you can group in corners. So if you have here one value here, one value here, and one value here, let's say 1, and one value here, one value here. Because these are actually like in a sphere, or like are connected in each other, we can do this grouping. We can group this corner with this corner, with this corner, and with this corner. So these are, all of them are grouped together. This is a valid way of grouping these together. And that's it. That's it. That's all what is very important about grouping. Even though it may sound a little bit too much now, but when we are going to apply these principles, it's going to become very easy. Now, the final rule, there should be as few groups as possible as long as this does not contradict any of the previous rules. So it means we should always strive to have the least amount of groups, meaning least amount of groups that covers all of the ones. So it does not contradict any of the rules that we have stated. That is very important, because if we apply this rule, it means that we have the most simplified expression, meaning meaning that we have the cost is the least and also the performance is the highest. Okay, now let's apply all of these principles. Let's take all of the theoretical on the side and let's actually apply it. So now let's do the grouping. So group, we see here that we can group these two together as a 1, and group these together as 1, as a 2, as a 1 group. So we have a group of 2 and a group of 2. Okay. Now we want to learn how to actually write the expression after grouping together. So now we have decided that this is the best grouping that we can come up with. Now how to write the expression for it? Well, you look at the group. Here this group, you look at what is constant along this group. So you see here A here, which is this, you have 0 and 1, but here is 1, here is 1. And here it is, B is changing along the group. So here, when you go from here to here, B is changing from 0 to 1, or from 1 to 0. However, A is constant along this row because it is in the row itself. Then we look for something that is constant, and if it is 1, we write the variable itself. So here the variable is A. And then we look for the second group. This is the second group. The second group, we have, what is constant here? We see that A is changing from 0 to 1 or 1 to 0. However, B is constant along this. B is not changing along this column. And it is equal to 1. If it is equal to 1, we write the variable itself, which is B. Then we have decided the variable for each, or the expression for each group. Then we just write it directly. So we have A, and then you have OR. You separate them between OR, and then you will have, which is OR, which is plus, and then you will have the second, which is B. So then you have this table could be very easily represented by this variable, by this expression, which is A or B, A or B, which is just an OR gate. An OR gate is just representing this table. And if we look at the table itself, you see it's actually just an OR gate. You have when 1 is there, it is 1. When 1 is there, and when both are 1, it is 1. When both are false, it is false. So it's just an OR gate. Now the example is very simple, but when you go to 3 variables, 4 variables, it becomes more complicated, and the need for this method is apparent. So now let's go to this example to illustrate it again. So again, we construct the k table, which is, or the k map, I guess. So going over like this, then we choose A to be here, which is 0 1 0 1, and then we have 0 1, and then we have B, B, yes, okay, and then we have 0 1, then we have 2, then we have 3. Okay, then now we fill in the values. We have 0, then 1, then 0, then 1. Okay, now we would like to group. Again, I think it's obvious that the only grouping possible, or the largest group possible, is actually just 2, which is this, which is having this group. And then you could say that the function is equal. Again, we look at the group itself, we see that A is changing along the group, but B is constant, so it means it is equal to B. Which is, let's verify with the truth table. When B is 0, it's 0. When A is 0, it's A0. When 0 is 0. So it is true. Now I would like to play a scenario that you actually made the wrong choice, or group incorrectly, or let's say incorrectly, not the most efficient way. So let's say instead of grouping this way, you decided that you would like to group them individually. So group this, which is a group of 1, which is fine to do, and a group of 1. So then you will look at each variable. Well, you look at each one of these. So you see F will be equal. So the first group here, group of 1, it will be A complement B. And the second group will be equal. Here you see A is constant because it's just one cell. Everything is constant. You will have A, which is not complement, and then you will have B. You have B. So then the function becomes A complement, and then you have B, and then you have OR A and B. Well, as I've told you, this is actually not the best way of doing it. Even though it is technically correct, it's just the sum of products, but it's not what we are looking for. We are looking for the most simplified way, the least significant or least costly way of doing this. So we can see that it's very easy to simplify this. Just taking B as a common factor. You will have A, and then you have OR A, which is equal to 1. So you have B OR 1 is equal, not OR, and a 1 is equal to B. So we arrived at the same exact answer, but we had to do a couple more steps using Boolean expression or Boolean simplification, Boolean algebra simplification to get this answer. But choosing the correct group has led us exactly to the same answer without doing all of that. So it's very important to choose the groups that cover all ones and the least amount of groups that is possible. So with the practice, it will become much easier. So now let's go to actually doing the 3 variables, which is what we are. So this is not usually done with 2 variables. The K-map method is usually done with 3 variables. 3 variables, because 2 variables is very simple. You can do it with Boolean expression simplification, but 3 variables gets a bit more complicated. So now first begin with it. I would like to explain what is this. So this is another way of actually another way of representing the function itself. So this notation means here, this notation mean that it is a min terms of the function. Min terms mean that when this is 2, it means that when this is 2, it means that the value of it is going to be 1, not 0, 1. So let's try to represent this using the same way. So we have here f of A, and then you have B is equal, and then you have min terms, and then you have here. So here we look at the ones. So the ones is going to be 1 here, and then here the 1 is going to be 3. So when these two first is equal to 1, is going to be equal to 1. When this is equal to 3, is going to be equal to 1. So this is one way of representing it. So instead of using The truth table we're representing using this notation. Okay. Now after knowing what is actually this, now let's see how to actually construct the K-map for three variables. So let's begin. Bismillah. So we have this and this. So 1, 2, and then we have 3. So first we choose one variable to be here on the side. So we have here 0 and 1, exactly like two variables. Then here the difference is going to be here. So here we want it to be in a specific order. So first we have two variables, which is y and z, which is here. First we write 0, 0, then 0, 1, then 1, 1, then 1, 0. So you may ask, why did we jump to 3? So we have here in binary this is 0, then we have this is 1, and this is 3, and this is 2. So why did we jump? Why did we make this jump? Well, we made this jump because of the way actually the K-map works. The K-map works in a way that that's one property of it is that the two adjacent cells. So you have here m of 0, and then you have m of 1. That two adjacent cells here, when you are grouping them together, there must be at least, like, there must be in the rows and the columns, there must be one variable at least that is constant along this. So let's say, for example, that we did not do this. Let's say that we say 0, 0, then 0, 1, then 1, 0, and then you have 1, 1. So if we have here one cell, and then here we have one cell as well. We have here one cell, and we would like to group these two cells together. So if we have here 1 and here 1, and we would like to group them together, look here what is happening. So here you have the y, and then here you have a z, and then here you have a y and then z. So the y from 0 became 1, and the z from 1 became to 0. So both of them are changing, which is not the thing that we want. We want one of them to be constant at least. So this is the way we actually construct it for three variables. So you have just to memorize it, that you have to begin 0, 0, then 0, 1, then 1, 1, then 1, 0. And again, the reason for it is that because we want one variable to be constant. And if we do not do it this way, then it will be wrong, or at least hard to do, I think so. So now let's actually do it. So we have here, let's just make this a bit smaller. So now let's do it. Now again, this is my preference of doing things. So here, what I told you about writing these on the side of the table is just to help you actually write the numbers so you do not get confused. So here exactly this, I'm gonna do exactly the same thing, which is here. So you have 0, then you have 1, then we have, so here exactly. So we have 0, then 1. Here, instead of writing 2, we write 3, then you have 2. You see here, because this has became 3, then became 2 again. And then you have 4, then 5. So then here, instead of 6, you write 7, then you have 6. So we just switch the places of these together. So instead of 2, we write 3, instead of 6, we write 7. And that's it. So then we fill in the table. So let's fill in the table. So we have 2 is here, then 3 is here, and then 4 and 5. Okay. And the rest will be 0. And the rest will be 0. So now we'd like to choose two groups, or at least any number of groups that covers all ones and will be as large as possible. So we see the only two possibilities we have, or the only possibility we have, is just here you have the group of 2 here and a group of 2 here. And that's it. That's our work for grouping is done. Now we would like to write the function itself. So f will be equal to. So first write the expression for this group. You will have here x is constant. X is not changing along this row, which is x, x, just the variable itself because it's 1. And then you have here, you look at the one in the columns here. You see that from this to this, we see that the y is constant. Y is 0. However, the z is changing, so it became from 0 to 1. So we say that y, but instead of y, because of it's 0, we say it's y complement. And this is the expression for the first group. Now the expression for the second group, we see that the x is complement along this row, so we write x, and then you have complement because it's 0, and then you see that the y is constant, so you have 1 and 1, so you write 1. So then we write the expression, you have x y prime, and then you have or x prime, or x complement, and then you have y. And that's it. This is the expression. This is the form of it. And that's it, man. So this is the way of actually writing the for 3 variables, writing the k table or k map, I guess, for the 3 variables. Now let's do one more to just make sure that we understand the concept, and then we go for 3 variables. For 4 variables. So Bismillah. طيب, here we draw the table itself, going along here. 1, 2, then we have 3, and then we have 0, 1, and then we have x, and then 0, 0, 0, 1, and then 1, 1, 1, 0, and then here we have y and z. Okay, then again 0, 1, and then you have 3, 2, and then you have 4, 5, 7, 6. And this method is just mostly temporary, just till you get used to the concept of this being flipped around, and then you get used to it. So you do not have to write this every time. But my advice is that you write it each time, because sometimes you get confused. You look at 7 or you look at 2 and you are a bit confused. Where should I write it? Either here or there. So this just make sure that you do not get lost when placing the ones. So we have 3 is here, and then we have 4, and then you have 6 and 7, which is here, and then we have 0, 0, 0, 0, 0. Okay, this is a very good example to illustrate some of the things we said. So the first thing, is obvious thing, is just to group these 2 together, which is vertically like this. Then the obvious thing is, now you could do it in a different way. First, you can group these together here, and that would be a good way, but you still have 1 here that is left. So what is the solution? First, remember what I said about things that is being wrapped. So imagine like it's a cylinder. So it's a cylinder. So if you wrap to these two sides, these will be adjacent to each other. So this will be adjacent to this, and this will be adjacent to this. So it means that we can group this in this way, which is this way and this way. So that is actually a valid way of grouping them. So we have 2 groups now. So now let's write the function. So we have f is equal to, now we have this group. So here x is changing, but y and z is not. So y and z, and then you have or, and then x is constant. So we have x is constant, and then y is constant as well, which is the z1. And that's it. That is the way of doing it. You look at what is constant and you write it, and if it is 0, it is the complement. If it is 1, it's the variable itself, and that's it. Very, very, very simple. With a bit of practice, you will see that how easy it is. It becomes like a game, trying to figure out what is the best way of grouping them. Now let's see how to actually do it for. Is it still 3 variables? I guess so. So let's do one more example, just to make sure that we get the topic or the concept right. You have here, you have going across, going across 1, 2, then we have 3. Again, here you have 0, 1, here you have x, and then you have y, and then you have 0, and then you have 0, 0, 0, 1, 1, 1, 1, 0, and then we have here, again, you write 0, 1, 3, 2, then you have 4, 5, 7, 6. Okay, now you write, here you have, what is that? We have 1, here 0, 0 and 2, which is here, and then 4, and then 5, and 5 and 6 as well. Okay, so it's correct. We have 0, 0, and 2, 2, and then 4, 4, and 5 and 6. Okay, correct. And then we have this, this, this. Okay, now we have, you can see a couple of ways of grouping them. Well, Also, one idea that came to me, which is actually not the best way of doing it, is what is that? Where is one way is just doing this way. So we have grouping these two vertically and grouping these two vertically, but that wouldn't be the best. The best way of actually doing this is just to group these in a way to make four. Remember that you can group in 1 or 2 or 4 or 8 or 16. And the bigger the group is, the better, because you have less variables in the group itself. So this is the way to group it, actually, the best way to group it. So this is the first group, and the second group would be something like this, which is grouping these together. Okay, now let's write the expression for it. So the first one here, which is the 4 group, you see that x is changing, and then you have the y is changing, but the z is constant. So z prime is constant, or z constant. And then you have the second variable, you see that x is constant, and then you have the y is constant as well. Y is constant, which is 0. So then the function f is equal to, you can write f of x, y, and then you have z is equal to z complement and then x or complement. So you can notice here that the bigger the group of 4 yielded 1 literal, which is 1 variable, and a group of 2 yielded 2 literals. So it means that the bigger the group, the better it is. So a group of 8, in this case, for 3 variables, would actually yield 1, just exactly 1, no variable at all. Yeah, that is the general rule. You need to have it as the biggest group you can have. Okay, now I would like to go to 4 variables, then come back to this example. This example illustrates a very good use of K-maps as well. So let's go to 4 variables. Okay, 4 variables is exactly the same, but it's a bit more complicated in the placing part, because you have to follow a specific way as well. So we have first going over here, so we have 1, 2, 3, and then you have 4. Going over here, 1, 2, and then we have 3. Again. Now here we have to choose 2 variables rather than 1. So we have choose w and x, and then here we choose y and z. Okay. Then the first one is here. It is exactly the same, 0, 0, and then 0, 1, and then we have 1, 1, then 1, 0. And here it is exactly again the same, which is 0, 0, then 0, 1, then 1, 1, then 0, then 1, 0, I'm sorry, then 1, 0. So then here the writing is very important as well. Here, as it gets more complicated, here you have 0, 1, and then you have 3, 2, and then you have 4, 5, 7, 6, and then here you jump 1 row, because here you see there is a jump. So you go to 8, 8, 9, and then you have 11, 10. So here these are switched. Then you have 12, 13, then instead of 14 you write 15, and then you have 14. And that's it. So this is the way of actually writing it. This method is very important when you go to 4 variables. Very important. Because man, the amount of times, the frustration that caused me not writing this, it's not worth it. So either you write it or you be very careful in placing the ones. Because a misplaced in one cell makes the whole expression wrong. Okay, now let's write it. So we have 0, and then we have 1 and 2 and 4 and 5 and 6 and 6, and 6, no, 6 is here, and then we have 6, and then we have 8, and then you have 9, and then you have 12 and 13, and then you have 14. Okay, time. So you see here we have, this is the table we come up with. So the rest is actually 0. So let's try 0, 0, 0, 0. Then we look what is the maximum group that we can have, the biggest group that we can have. Again, I would like to remind you that there's the possibility you can group is 1 and 2 and 4 and 8 and 16. Well, we could see that there's 8 adjacent cells that are against each other. So here, so let's group them together. So we have this and this and this and this. So this is one group of 8. And then we have again 3 here. So let's group this here of 4. So let's group this here and group this here. So this is a group of 4. And we still have 1 here. So let's group this here and group this here. So we have a group of 2 here. So in the end, we have 3 groups. One group of 8, one group of 4, one group of 2. So let's write the expression for it. So first, we have this. We see a group of 8. W and X is all of them are changing. You look here at the Y and Z. Y is not changing. Y is 0 and 0, but Z is changing 0 to 1. So the only variable that is constant is Y, which is actually Y prime because it's 0. Okay, now this grouping, you see here W is constant, which is 0 and 0, so we write W prime, and then you see that Z is not changing, it's 0 0, so Z prime. Okay, then you look at this group as well. This group, you see that W and X are not changing, both of them are 1, and you look as well, you see that Z is not changing, which is Z prime. So this is the expression. So the expression is, you can say that F is equal Y prime, and then you have OR. Let's see, is there a better way of doing this? I don't think so. There is actually a better way. I remember, there is a better way. I've seen a slide. Yes, I'm sorry. So there is a better way. So instead of writing this here together, so you can have actually a better group. So instead of grouping these two together, you can group it as a 4. So here you can have 4. So going over like this, and going over like this, and going over like this, and this. So this is the 4th group. So the 3rd group is actually 4. A group of 4. So here again, so instead of writing 3 literals, so we write 2. So this will be, you see here going over. So here, this is X is not changing. X is not changing, and what else? X is not changing, and Z is not changing. So Z prime. So let's write it now. So you have Y and Z prime, and then you have OR X and Z prime. And that's it. That's it, done. I think this is the simplest form of this expression, of this truth table, or this function, I guess. Again, and sometimes it's not obvious. This is maybe a second time I make a mistake in it on this exact problems. So sometimes it's not obvious, but always look for the group that is actually makes it the biggest group that's possible, even if they overlap, because having a bigger group, mean that you will have less literals, meaning you have less variables in the function, which is always better. You will have the simplest form, so you don't have to do any simplification. So probably this function that we have reached is actually the simplest expression we can reach using either Boolean algebra or any other methods. Now we have one more example to show the case of the use of K-map method using the function itself. So instead of actually the truth table. So let's give this a try. So we have 2 parts of this question. We have A, which is express it in terms of minterms. So how to do this? Well, the definition of minterm says that in each term the function or each variable has to appear once, at least once. So here the function, we can write this function as, so we have f of A, and then you have B, and then you have C is equal to. So this is the order we have to follow, which is A and B and C. Okay, which is here, appears here exactly, because the order matters a lot. Then we have this function is equal A prime, and then we have C, and then A prime, and then you have B, and then you have or A, B, and then you have C prime. No, it's B prime here, I'm sorry. And then you have B, and then you have C. So this is B, and then you have BC. Okay, so we have this is the function we have. So to get it, to express it as a sum of minterms, all we have to do is just to make sure that the 3rd variable appear once in each term. So what does that mean? So let's try to do it. First, So we have this is this. So let's look at the first term, which is a prime, and then we have c. So what is left here? What is the one thing that is, what one variable that does not show, which is the b. So what we do is we multiply by b prime, and then you have or b, which is which is just 1. So this is like an identity. So it is like multiplying a number by 1, which is exactly the same thing. Here it's exactly the same thing. You have this and then and 1, which is just the same as a prime c. So it does not change the value of the variable. So that would make it a prime, and then you have a complement, and then you have b complement, then c, then or a complement, and then you have b, and then c. So that's it. We got it into this form. You see that each variable appear at least once, or I guess exactly once, one time in each variable. So this is the definition of sum of minterms, and we do it for each of these variables, or we do it in each of these terms. So let's do it. So we have the function f is equal. So this is the first one we have done it, which is a prime, and then you have b prime, c, and then you have or a prime, then you have b and c, then you have or. Here we see that we have c, so the c prime, and then you have or a, and then you have b, and then c prime, then you have or. So this is already ready for us. So that's it. And then you have here a has to appear at least once, or exactly once, and that's it. That's it. And again, we have to make sure that the order is correct, a, b, c, because changing the order means that you have the incorrect value. Now we want to write the values. We want to write the values for it. So one, it is actually true. So because it is actually the minterms. So here what we do, we see one each time when it is complement, it is 0. So this is 0, this is 0, and this is 1. And then this is 0, this is 1, this is 1. And this is 0, this is 1, this is 0. And so on. We do it for all of these values. Sorry, here 0, here 1, 0, 1, 0. And then 1, 0, 1, and then you have 0, 1, 1, and then you have 1, 1, 1. Okay. Now we write what is the actual numbers in decimal. So we have here 1, and then here we have 3, and then we have 2, 2, and it is fine that they are repeated. And then you have 5, which was 4 and 1, and then you have 3, and then we have 7. So then, writing this function, it will be equal. So this is just done. This is the first one is actually done, which is the sum of minterms. But this is just an extra step to actually mention, to write in this form. And c is equal, and sum of minterms. Then you have 1, 2, then you have 3, then you have 5, and then you have 7. And that's it. That is the sum of minterms. Find the minimum sum of products expression. Now here, b, what we need to use. So this was just a. Now let's do it for b. So here we're going to use the k-maps. So let's see it. So first let's draw it. We have 3 variables, so let's draw the k-maps for 3 variables. 1, 2, and then we have 3, I'm going over. So we choose a to be here, which is 0 and 1, and then we choose b and c to be here. So we have 0, 0, 0, 1, and 1, 1, and then you have 1, 0, 1, 0, again 0, 1, and then you have 3, 2, 4, 5, 7, 6, and now let's write the values. So we have here at 1, which is here, and 2 and 3, which is here and here, and 5 and 7, which is 5 and 7, which is here, and then you have zeros here. Now let's write the values again. So now let's actually do the grouping. So it's very obvious that we can group this in 4. So one grouping is 4, and then the other grouping here is in 2. So let's write the expression for this group. So this group will be equal. First you see that a is not constant, and then this we have c, the only thing is constant. So d is constant. And then the second group, which is this, you see that a is constant. Here a is constant, which is a complement. I'm sorry, this is, yeah, here it's not complement, I'm sorry, this is wrong. So here it should be you see that here here you have B and then you have C, B and C. C and C becomes, it does not change from 1 to 1, so it should be C, not C complement. And then here you have A complement, which is this, and what as well? You have A and A, which is B and B, B and B, and C and changes, so B, so B, B, B. So then the function becomes, which is the simplified function, you have C, and then you have or A complement, and then you have B. And that's it. That is the simplified function. You look from this whole function, either this one or this one, you see we have simplified only to this two. So here only one gate, which is the OR, and the other which is the AND, and then also you have a NOT, instead of using this. So here you have how many terms? You have 1, 2, 3, 4, 5, 6. You can calculate from here. You have 5 terms, and that means that you have five times you have an OR gate, and then you have also a lot of AND gates, three input AND gates. So that's a very long expression to actually now to implement it using gates. But doing this way, you can see how much is simplified using this, just the K-maps method. And that's it. Hopefully that you got the gist of the idea, and that how can we actually implement it, and what is the use of it, and also what are the rules of actually grouping, and how to actually implement, how to actually use them in solving problems. And that's it. Thank you for listening.